Okay, so yes, you've got that handout, the nature of friction. We've spent a few minutes picking out the important things. These are what I deem to be important. If you choose to write these down, that is wonderful. If you choose to sit back and watch, also wonderful. If you choose to write down what you think is important of the what I think is important part, also wonderful. You do what works for you. I will post these to Schoology later in the period. Okay, so nature of friction, or as I like to say, well, here's where things start to get a little rough. Yeah. Okay. So yes, as I think it was Jake's group pointed out, friction is a force that resists motion, resists change. Friction always resists motion. Does there have to be motion for there to be friction? No. It always involves contacts that are in contact with each other. There can be no friction if there is no contact. Okay? There can be no friction if there's no contact. Air resistance actually is a type of friction. Your football or whatever you're throwing is in contact with the air. So, some causes of friction, as Chris was pointing out at the end here, an object actually deforms its surface and vice versa. So what they're saying is, if you put something real heavy on a table, right? You put something real heavy on a table, and that's not going to work because they're not in contact with each other, right? It actually makes the surface dip microscopically. Okay? And so it's sort of got an uphill battle. Kind of, it has to plow through that uphill. Okay, a plowing force required to move the object over the deformations. There's actually a lot of controversy in the scientific world about friction. They don't really get it. They're still working on it. Yes. For the most part, everyday, regular friction, yeah, we get. It's sort of the complex kind of stuff that we don't quite understand quite yet. Irregularities interlock and offer resistance to movement. The surface of that block and the surface of that table, so what they're talking about there is the bottom of that wood block actually is kind of not smooth, and neither is the tabletop, right? And so these little bits and pieces sort of lock together, right? Kind of like plate tectonics. You guys know about that, right?
Not really. No.
Plate tectonics is like, the Earth's crust. I'll get you, Jake. The plates, as they move around and they sort of go underneath one another, and that's what causes earthquakes. They kind of lock together, right? And they twist and they bend, and then eventually they give away, and then that's when they get that earthquake. Jake's got a question.
I was just wondering, like, you said that scientists are confusing complex friction, but like, how much more complex can you get than it is?
Well, they're talking about like very finite differences. Like a space shuttle type of like very highly technical, very precise kind of applications. Not like, do we put gravel on the roads or do we put cooking oil? Talking about friction, I probably shouldn't mention this because I like to do it in grade 12, but I'll tell you guys because you're my friends. Mr. Schmidt's brother, his older brother, is a professor of, I don't even know what the actual thing is. I could say biomechanical engineering, but he's basically, he's trying to create a fake knee, an artificial knee. And as part of his studies, they were doing, they were looking at this lubricant that they found in the knees, and they ordered some human body parts to study on a real knee. They can do that at universities. And when they got it shipped, they actually made a mistake, and instead of shipping knees, they shipped eyeballs.
Oh.
Yes, so they had this collection of eyeballs, and his research partner's father was actually an eye doctor, and so they got talking about this, right? And they discovered that, they did some research, they discovered that the lubricant that they were looking at for knees actually also exists, the protein exists in your eye. Okay, so they started to do some research on this, and they actually measured the frictional coefficient of eyelids on eyeballs. Okay, they found the mu value of eyelids on eyeballs, and then they put the lubricant, this natural protein, they increased it, put it in the eyeball, and they found that it actually decreased the frictional coefficient. They're actually in trial now over in Europe. He's got a company, and they hope to be, Visine, they hope to create the world's best eye drop to stop dry eye irritation. Okay.
Oh, that's nice.
So But can you imagine frictional coefficient of the eyeball on the eyelid? I Skyped him in once and he showed us how he did it, right? Took the eye and went. I can see if I can do that again with you guys. I'm sure he would. Yes. He's a professor now at the University of Calgary, and that's what he studies. Yeah. Okay. So starting friction is the maximum frictional force between stationary objects. I don't remember who it was. Someone over here said that, right? Starting friction is the maximum frictional force between stationary objects. It is always greater than or equal to sliding friction. Sliding friction is the frictional force between objects that are sliding with respect to each other. There's also rolling friction. Now, rolling friction is very complex. And I think I've already mentioned this to you. We're going to assume that everything slides and it doesn't roll. When we did the rolling the ball down the ramp lab yesterday, was there some friction involved? Yes. Was it rolling or sliding friction? Rolling. Okay. It's kind of complex. It has to do with angular momentum and the density of the ball and the diameter of the ball and all sorts of crazy things, right? So yeah, we're going to just deal with sliding friction. Okay, so some properties of friction here. Friction acts parallel to the surfaces that are in contact. It must be parallel and in the direction opposite to the motion or to the net force tending to produce such motion. In other words, if there was no friction, which way would it move? Friction is always opposite that motion. Friction depends on the nature of the materials in contact and the smoothness of the surfaces. I think that's generally understood, right? If things are really smooth, there's going to be low friction. If it's really rough, there's going to be more friction, like putting the sand on the icy streets in Dauphin, right? We want to increase friction.
We should do that.
They should do it again. You're right. They're getting quite slippery out there.
At McDonald's, they should do that.
Yeah? Did you have a little accident?
So you can get out. So you can
Oh, yeah. Up that little hill, eh? It's kind of, yeah. Yeah. Sliding friction, as Ali pointed out, sliding friction is less than or equal to starting friction. There are rare occurrences where the starting friction and the sliding friction are equal to each other. Friction is practically independent of the area in contact, and I'll probably talk more about this in the future, but there's a great deal of confusion around this. People think that large objects, like say for this example, the difference between a road bike tire and a mountain bike tire. People think that, oh, the road bike tire is big like this, more friction. Not true, actually. Okay? Has to do more with the nature, like how the road bike tire is very smooth, and the mountain bike tire is sort of knobby and kind of has those little sort of, bumps on there.
There's a greater surface area. Wouldn't that mean there's more area for the friction to act on?
That's true, but what it does is it reduces the pressure because it spreads it out. You know the old walking on thin ice, spread yourself out kind of thing? So if you've got a car with big fat tires and the same car with skinny tires, the friction's the same. It's the pressure that's different. So, yeah. Starting or sliding friction is directly proportional to the force pressing the two surfaces together. This is key. The force pressing the two surfaces together, well, that's simply the object's weight. Right? Heavier things have more friction. When you are trying to get up that hill at McDonald's there, you might see some trucks driving around town with a skidoo in the back. Right? Why do they do that? They can show off their cool skidoos, right? That's why they do it.
Yeah,
right?
that is true.
Okay, some of them might actually do it because they want more weight in the back of their truck. I actually had a friend of mine who used to drive around with a 200-pound block of concrete in the back of his truck in the wintertime. How come? Because it's a rear-wheel drive. He didn't have four wheels. He had four wheels. He didn't have four-wheel drive. Okay? Needed to add a little bit of weight to the back to increase the friction. Okay? The converse of this is if you're trying to reduce friction, if you can reduce the weight, reduce the amount of pushing force, well then you'll increase friction. You know those, they call them spoilers on the back of cars? What are they for? My dad always said it spoils the look. And you wonder where I got my sense of humor from. What's the spoiler at the back for? To make it look awesome, exactly, yeah. What does it do, Keelan? Yeah, it actually forces the rear end of the car down so that there's a greater amount of friction they can accelerate more. That's right. That's why
Celery sauce.
some of those F1 cars will actually go airborne if they don't have that wing on the back kind of thing. Yeah. Okay, so Keelan was talking about the coefficient of sliding friction. Here is the formula. It is defined as the ratio of the force of sliding friction to the normal force, and it's conveniently written as mu.
It's a mixture of a Y and a U. And
Yeah, it's a Greek M, right? It's written like that. It's a U with a tail on the front. Mu equals FF over Fn. Friction force over normal force. Okay? So the friction force is how much friction there is. The normal force is the object's weight. Now, people get confused a little bit about this. The mu value is dependent upon the surfaces. If you look at your sheet, on the back side, there is a table of mu values. Okay, so like steel on steel, 0.74. Okay, that's just what it is. Steel on steel is 0.74. Glass on glass is something different, so on. They tend to be numbers between 0 and 1. If you get a frictional coefficient greater than 1, you've got a lot of friction. Okay? So, the mu value is set by the nature of the materials. The normal force tends to be set by the weight of the object, right? And so, the mu value and the normal force create the friction, so to speak. It should probably be more written like FF is equal to mu Fn, which is perfectly acceptable. But they like to talk about this ratio thing.
So what would have like a friction value greater than 1?
Oh, I don't know. Is there any listed there? Yeah. Like Teflon on Teflon, that's pretty slick, 0.04. Rubber tire on a dry road is 0.7, right? So think about a rubber tire sliding across a road. Fair bit of friction there, right? Like you would need something like gravel versus Velcro kind of thing to get greater than 1, right? Or two gravel covered objects. Maybe you've got gravel glued or sand glued to sand or something like that. I don't know. Okay, so what I'm going to do is I'm going to show you how a couple of these examples work. Now, I think I have these copied for you. All right, let's have a look here. Riley will be with us in a moment. So example number 1, a box with a mass of 175 kilograms is pulled along a level floor with constant velocity. The words constant velocity are your new best friend.
Yeah.
It makes the problems a whole lot easier. The words constant velocity.
Okay.
Why do the words constant velocity make the problem a whole lot easier?
Because it's going to be a straight line on the graph. That's constant.
Zero acceleration, which means that, right, a box is being pulled along a floor like this, right? There's the floor. Here's the applied force. Here's the friction force. There is no acceleration, which means that the net force is 0, which implies that the applied force is equal to the friction force. That is important. The words constant velocity mean that the applied force and the friction force are equal, just opposite directions. Will there be instances where there is an acceleration and it's not a constant velocity? Yes. Will you then have to use F net equals MA to find F net and then find FF? Yes. But so far, let's just start with the easy.
What's the free dots mean?
Therefore.
There.
Okay, so the box has a mass of 175 kilograms, so that is the weight force, and we have the normal force up. We are at, no, it gives us the coefficient of friction, and it asks what horizontal force is exerted in pulling the box. Which one of those four forces, Fn, Ff, Fw, or Fa, is it asking for? Correct, Joey. Fa. What horizontal force? They are looking for the applied force. And as I pointed out, the horizontal applied force is equal to the friction force. So if I can find friction force, then that tells me the applied force. Can I find the weight force? Yes. You are almost always, from here on in, the rest of your physics career, you can almost always start your problem with Fw equals mg, because it almost always matters. Okay, and it's almost always worth a mark, too. So 175 kilograms times 9.8. Sorry, I don't have that one memorized. 175 times 1715. Is that what you got? Okay, so in other words, if we put that box on my Newton scale, it would register 1,715 newtons. Now, I also have the coefficient of friction, so now I can go to mu equals FF over Fn, and again, I strongly encourage you to write the formula, and write the next step right below. The mu value is 0.34. The friction force I do not know. The normal force is equal to, now I haven't actually calculated the normal force, but I have calculated the weight force. Is the weight force and the normal force equal to each other? Yes, it is. How come? Because the object ain't going up and it ain't going down. It's staying still, right? The net acceleration is 0. They are equal to each other. When will the weight force ever not equal the normal force? When it's on an incline. And we'll get into that in grade 12. Can't remember now. It's been so long. Okay, so yes, this means that the normal force is also 1715, so I put that in there, and I calculate my friction force. 1715 times 0.34 is 583.1. That is my friction force. Therefore, the required applied force is also 583.1 newtons. I think these problems would be a lot cooler if I were doing them on like one of those blue boards with chalk, and I had like a big mustache and a beret and glasses. Because they do this stuff. Any questions to go along with that question there, that problem? Yeah. Okay, I'm only going to do one more. This one is a little bit more challenging. A box with a mass of 46 kilograms is pulled along a level floor at a constant speed by a rope that makes an angle of 30 degrees with the floor as shown. So it's one of those. If the force on the rope is 260 newtons, what is the horizontal component of the force? What is the normal force? And what is the coefficient of sliding friction? I think you have it all there, including the picture. Am I right? Excellent. So we can continue. I'm going to make this smaller just to sort of get it out of the way a little bit. Okay. So what is the horizontal component of the force? So 260 newtons at an angle. We've got a 30-degree angle. This is my horizontal component. Hopefully you remember that FH is equal to F cos theta. So that's going to be 260 times the cosine of 30 degrees. Is the horizontal component always going to be less than, or could it be possibly more than the applied force?
FH equals FA.
Sure, FA, yeah. The A is just a subscript. It doesn't really mean anything other than what force we're talking about. 260 times cos 30, right? Not that value. I get 40.1. Sorry, Riley, we had to start. I know my reason. I'm in radians. Radians are bad. Let's go to degrees and try again. 30 degrees cos times 260. It did seem a little low, yes. 225? 225.16. Okay, so all that means is that of that 260 newtons, 225 actually goes into pulling it sideways, right? And the greater that angle is, what happens to that value? Like if you make it much steeper angle, that number's going to go lower, right, Zach?
Yep.
Right? Like you're going to get more pull out of it if you make it as low as you can, right? Now, here's where it gets a little tricky. What is the normal force? Your first instinct might be to say, well, Mr. Bennett, it's 46 kilograms. Weight force is mass times gravity, and 46 kilograms times 9.8 is 450.8. newtons. All of that, why did I write 9 again? You might think all of that is true, and unfortunately you would be wrong. Brandy's off. She's like, not again. Why is the normal force not 450.8 newtons? The weight force is? Exactly. It's also pulling up. If the rope wasn't pulling up, then it's the table that has to provide 450.8 newtons of upward force. But the rope is also pulling up. Exclamation mark.
We have to use the thing.
No, but I've introduced you to the horizontal component, but there's also a vertical component. Exactly, Dan. Is that what you said? There is also a vertical component. Now, the vertical component, FV, as Keelan has pointed out, lifts up, and you'll notice that it is opposite the 30. Which of the trig functions has opposite in it?
Two of them?
No, which of the 3 trig functions, sine,
Tan.
cos, or tan, has opposite in it?
Tan.
Tan does. Which one has opposite and hypotenuse in it? Sine, right? So in this little triangle here, F and FV, right? Opposite, hypotenuse is the sine. So sine 30 is equal to my opposite, my FV, over my hypotenuse FA. And what do you know? I got FV is equal to FA sine 30. The horizontal is always the cos. The vertical is always the sine. Why are they always that way? Like, why is the horizontal always cos? What does the cos trig function have in it? No, cos has adjacent and hypotenuse. And the adjacent, if you're always talking about this angle down here, isn't the adjacent always going to be the horizontal one? Yep. And isn't the opposite one always going to be the FV, which is sine? So yes, I get FA sine 30. So in this particular case here, I'm lifting up with, it's going to be 260 sine 30. 260 times 30 sine is 130. Okay. I'll pause for a second. Watch close, you guys. This is tricky stuff. So what does that 130 newtons mean? How much force does the table need to push up? If the object weighs 450.8 newtons, if the upward force wasn't there, it would have to push up with 458 newtons. But the upward force is there. So does it push up with more or less 450? Less. How much less? 130 newtons less. It's really a net force problem is what it really is. Okay? So what you've really got is, you've got weight force, which is equal to 450.8. You've got a normal force, and you've got a vertical force. And that vertical component is 130. Okay, you guys got to watch.
Someone made a weird laugh.
I'll make a weird laugh right away. Then you might listen to me.
Okay.
There you go. Now you listen to me. Okay, so 450 newtons down. I got 130 up. I need to balance these. These things here need to add up to these things so that they total 0. So how much is the normal force? How do we write that using our formulas, says Anderson? Because now he's writing formulas. FW is equal to Fn plus Fv. Now, do we have to worry about signs here?
No.
Yes. Because the weight force is down, and really, this combination is the normal force, and it's up. Are they actually equal to each other? No, one is negative and one is positive. If I don't worry about the signs, then I don't have to worry about that. So the weight force is actually 450.8 newtons. It's actually down, but if I don't put a negative in there, then they have to be numerically equal. Normal force. The FW is 130, and when it goes to the other side, I actually make a subtraction, and I actually subtract, which is what I want. So my normal force is 450.8 minus 130, whatever that is, right?
So you didn't need the sign. Right?
Uh-oh, what'd I do?
Yeah, you do.
Yes, I need the sign. It was down up here, right? So 450.8 minus 130 is 0 to
Oh, were you
320.8,
Are you
right?
talking like sign, like S-I-N, or the
No.
sign like positive negative?
Talking about S-I-N-E, the sign, trigonometric sign, not S-I-G-N. Okay, so does it make sense that the normal force is 320.8 newtons? Does it make sense that the normal force is less than the weight force? Why is it less than the weight force? Because there's a vertical helping force. And oddly enough, if you increase this angle, the horizontal component decreases, but the vertical component increases, which actually reduces the friction. It's easier to push things if someone does what? Lifts them up a bit.
No.
Right? Okay. So that is the answer to B. Now my answer, what is the coefficient of sliding friction? I'm almost done, I promise. Part C, mu equals FF over Fn. How much friction force do I have? I don't even know. I do know, because the magic words constant speed are in there. If the object's moving at a constant speed, that means that the what is equal to the what?
Applied.
The applied force is equal to the friction force. Now, does that mean that the friction force is 260? Or does that mean that the friction force is 225.16?
Whatever it is.
It's this one. Don't start packing up.
I wasn't. I was opening the magazine.
Okay? The friction force is equal to 225.16 because friction force opposes motion. Which way is the motion? Sideways. That's the force that's producing the sideways motion. So, my friction force is that 225.16 value. My normal force is 320.8, and using that, I can determine the coefficient of friction here. It will be significantly more than the coefficient of friction between eyeballs and eyelids. .70. Again, your coefficient value should be between 0 and 1. If it's significantly more than 1, you have to question yourself, did I do this right? Is this just a made-up question?
If it's unit in newtons or...
Excellent question. Excellent question. What is the unit in? I usually don't get that far, but we have 2 minutes. What is the unit in? Hannah, what is the friction force measured in?
Newtons.
And the normal force measured in?
Newtons.
Now, when you do Mr. Friesen dimensional analysis, newtons divided by newtons cancel, and what you get is big fat newtons. The unit of frictional coefficient is newtons. Okay? There is no unit because it's newtons over newtons. It is a ratio. There is no... No, because there is no unit. It doesn't exist.
You can make one up.
Doesn't exist. All right.